Good afternoon, everyone. We'll just start with the session. Welcome to the session. In this session, we are going to talk about hardware accelerated VirtIO for network function virtualization. I believe many of us must have attended the session prior to lunch where we talked about performance issues with network function virtualization, and there were certain suggestions for improving the performance. So we are also kind of looking at that, and we also have a proposed architecture through which we want to improve the performance for network function virtualization using VirtIO. So we'll be talking about, we'll be looking at the performance issues that are related to VirtIO when we use network function virtualization, and we'll see how we can actually accelerate it using the hardware features. So today, me and my colleague, so I'm Varun Sethi, and my colleague Yashpal Datta, we'd be conducting the session. So following would be the agenda. We briefly look at what is network function virtualization. I think that this was adequately covered in the previous session, but still I'll just touch upon it briefly, and we'll just look at certain deployment scenarios. After that, we look at IO virtualization mechanisms.
So what's the point of it?
Thank you so much. So we start by looking at, briefly talk about network function virtualization. After that, we look at IO virtualization mechanisms. And after that, we would be actually touching upon Vhost-net. So this is the mechanism that we used in our particular test case where we ran an IP forwarding benchmark as a virtual machine. And we'll look at what kind of issues we faced and what was the workaround that we used for solving a functional issue, and plus also trying to improve the performance for that benchmark. And then finally, we touch upon an architecture that we would like to propose to improve this performance, which is based on using hardware acceleration. Okay, so typically, network function virtualization means that you're actually running various different network functions as virtual machines on top of a hypervisor. So what that allows you to do is that it allows you to kind of provision services dynamically. If it would be with a physical network infrastructure, this is going to be very costly, because to spawn a new service, you would require new hardware that increases cost, and plus also is going to add to the power consumption. With this, you can use the adequate, you can actually use the existing hardware to actually spawn the new functionality. And all these network functions are actually managed by the hypervisor. And this also offers agility and flexibility based on the load that you have to handle, based on the number of customers that you are having. You can actually scale up and scale down, or spawn new services, or kind of get rid of old services. So those are the kind of benefits that you get out of network function virtualization. So there could be two possible deployment scenarios for network function virtualization. One could be, in this case, what I have taken a server which is running multiple, say, server VMs. In one case, we are having a network appliance which is capable of spawning virtual network functions using the hypervisor. So this network appliance is actually handling, so it has multiple virtual machines which are catering to the virtual machines which are running on the server. In the second case, we have the network function which is actually running on top of the server itself, which is actually providing services to a server VM. So I think this was kind of discussed in the previous presentation where we talked about the inter-VM communication. But this particular scenario where you have a network appliance, this is kind of also, this was also something which we need to look at, because this is something which is going to be there in case of application delivery controllers, which are actually front-ending servers and are used for TCP connection termination and also SSL connection termination. So effectively, how the packet flow is going to be that you get a packet from the network, it goes to a corresponding network function, which is running as a VM. So the network function processes the packet. After processing the packet, it forwards it to the virtual machine. And when the virtual machine has to send the packet, it goes to the network function on the network appliance. It would process it and send the packet off to the network. And similarly, for the case where the network function is running alongside the servers, You get the packet in the network function, which forwards it to the VM, and subsequently from VM to network function, then off to the network. Okay, so in this, like, one thing to notice is that we are using a shared NIC, both for, in the servers as well as the network appliance that we're talking about. And so, like, the thing is that virtualization is required. We need to virtualize this NIC so that it can be shared across multiple virtual machines. So certainly I think we all would be aware that there are mechanisms like a full virtualized mechanism, or there could be a VirtIO based mechanism through which you can do it, and VirtIO being a bit more efficient because you have front-end and back-end drivers through which the guest networking driver, network interface driver can interact with the host driver, right? And making packet transmission more efficient. And in case of VirtIO, the communication between the front-end and the back-end driver happens using vert queues. So there are multiple such interfaces that can be supported with VirtIO. You have the block, the networking, and the transport mechanism is basically VirtIO PCI. Okay, so like in this particular slide, we actually show how VirtIO networking is going to work. So in case of QEMU, a virtual machine, the emulation for the VirtIO NIC is happening in the QEMU user space process, right? So the packet goes from the guest OS to QEMU, and then it is forwarded to the turn-tap interface in the host, from where it goes to the bridge, and finally to the physical Ethernet device, and to the network from there on. So as I just mentioned, the emulation or the backend driver is actually sitting in QEMU over here. It's a bit inefficient because you have to kind of switch to QEMU every time you need to transfer the packet. So you have to switch from the guest state to the host user space for this particular processing. With Vhost-net, we avoid the overhead of QEMU processing by emulating the networking functionality through Vhost-net running in the host kernel, right? So over here, as we can see, we are bypassing QEMU, and the packet transfer is happening directly from the guest OS to a vhost thread, which is there in the host kernel. So this is more efficient than the VirtIO networking being emulated in QEMU as such. Okay, a bit more details on how vhost functions. So in case of vhost, you have a vhost thread that gets created, which is running in the host kernel, right? And it is servicing. So each VNIC is virtual NIC, VirtIO VNIC is having an RX queue and a TX queue. So this vhost thread is handling both the RX jobs and the TX jobs on behalf of the guest VNIC, right? And after processing packets or receiving packets from the guest, the vhost thread is going to send them across the tap socket, from where it gets forwarded to the bridge and to the Ethernet. And in case of the RX case, the packet is received by the Ethernet driver, host Ethernet driver. It's forwarded to the bridge, then it goes to the tap socket, then it goes to the vhost thread, and then finally to the VNIC, the virtual VirtIO NIC sitting in the guest. So how, like, the vhost thread that gets created it's actually created through an IO control interface through QEMU. QEMU invokes an IO control to actually create this vhost thread in the host, right? And as I just mentioned, that vhost thread is going to handle both the TX and the RX jobs on behalf of the VirtIO NIC, the guest VirtIO NIC. Okay, so in our setup, we actually saw an issue with the RX processing. Specifically, we saw that the Vhost-net RX processing actually becomes a bottleneck. So I will just briefly touch upon how the RX processing works in case of Vhost-net, and then we would actually also talk about the workarounds and the proposed architecture to handle these issues. So this is a complete kind of a blow up of how the RX packet processing would happen in case of vhost.net. So initially, like we have the physical NIC which is receiving the packet. So we have the host driver routines that get called, and then you have the NAPI processing, which happens on behalf of the host driver, right? And so the entire path which is marked in green, like with the green arrows, is actually happening in the for the interrupt, hardware interrupt, and then after the hardware interrupt, you have the soft IRQ processing that is happening, right? So you have the poll routines for the network driver that get called, and then finally, once the packet is received by the driver, now it has to it has to forward it to the guest VNIC. So first, it has to send it to the bridge. So again, if you see, like in the previous slide, we were still in the host driver routines, which were being invoked in the as a part of the soft IRQ processing. And after that, when the driver has to forward it to the bridge, again we are still in the soft IRQ processing. If you like, this is the entire bridge processing that is happening. And after that, when the bridge has actually been able to process the packet and it identifies that it needs to be forwarded to a particular guest tap socket, that again happens in that particular soft IRQ processing itself. So once the packet is forwarded to the tap socket has to inform the vhost thread that there is an RX job for it to process. So it would actually wake up the vhost thread. So once the vhost thread is woken up, so there are a few checks for the vhost thread. So finally, it will actually see that there is some job for it in the work queue, right? So once if there is a job which is available, it will dequeue the job, and then the RX processing is going to start in the vhost.net driver, right? So this is the entire processing that happens in the for the RX in the vhost.net driver. So so this is handle RX is the main routine that gets called. So in the handle RX routine, it actually checks so we are dealing with the tap socket here. It will see whether there is data available in the socket. If yes, then the entire processing is going to happen over here, and then we're actually going to copy the data from the tap socket to the word queue. Word queue has the buffer descriptors enqueued by the guest, where we need to copy the data. So this data needs to be copied over there. So once the data is copied, so there is a check over here again, where we see, like, if we have handled. So there is a specific budget defined over here. So why do we have this? The thing is that the same vhost thread is supposed to process the RX and the TX jobs. So in case there, we have actually processed a significant number of jobs, we break out from here and see if there is another work which has been enqueued for us. It could be a TX job also, right? So if we do not do this, then if there are many packets, for example, coming in, then we'll be kind of stuck up here. We'll never break out from here and go for the next work item which has been queued. So this check ensures that after processing a specific number of packets, we break out from here and we move to the next processing. Okay, so till now we just touched upon the details of slight details of VirtIO, and then we saw like how vhost.net works, and specifically the RX side processing. So because that's what is, during our benchmarking, we saw that actually became a major bottleneck, right? So we'll see what kind of issues we can encounter when we are running an NFV network function virtualization use case with VirtIO. So again, coming back to the deployment scenario, I've taken the deployment scenario of a network appliance which is interfacing with the server VMs, right? So so in this case, I have this network function running, network function 3, which is running on the network appliance interfacing with the VM3 in the server. So in case of normal packet transfer, so as we could see, that packet comes in and goes to the server VM, and again from the server VM it goes to the network function and to the network. But if there is a packet flooding, right, Now suppose, because this interface is shared across multiple VMs, now if there is a case where I'm getting multiple packets for this VM, right, and there is packet flood, host is going to keep on receiving the packet and it will try to forward it to the VM. But say this VM is saturated, it's not able to handle the packets, right? So the packets, although are being received from the physical interface, they are being forwarded to the VM, but the entire system is saturated. VM is not getting a chance to consume those packets and maybe forward it to the server VM. So we are actually looking at, so packets are being subsequently dropped here, right? So the system is not progressing. Packets are received, but packets cannot be forwarded to the server VM. So it's kind of a denial of service that happens, and that's what we kind of encountered in our scenario. So this is the test setup that we used. So we have a guest KVM guest running, and so the guest had two VirtIO interfaces which were serviced by two vhost threads in the host. And then each of these vhost threads were actually connected to a tap socket and a bridge. And there were two bridge instances, each talking to a particular physical interface. So there were two 1G interfaces which were available on the system, and we had a bridge connected to each of these, and there was a separate tap socket for each of the vhost instances. So essentially, we were running an IP forwarding application here, the SMP guest. So the IP forwarding application was supposed to receive packet from one particular interface and forward it to the second interface, and then subsequently from this particular interface, it would receive packet and forward it to the second interface. So in this case, we could actually see that at a high traffic rate, the traffic, and we were having this the packet generator framework, which was basically generating the packet. So at high traffic rate, we could see that the RX rate on one particular port actually dropped to 0. So we were not getting packets in one direction at all. So although one particular port was receiving packet, but the other one was not. So on further analysis and like a lot of debugging, we could actually figure out what was happening in the system. So packet flooding, or like the packet generator was sending a continuous stream of packets. Now packets were being received by the physical NIC and then forwarded to the driver. Driver was forwarding to the bridge. Because the entire system was consumed mostly in the soft IRQ processing, the VM was not able to pick up packets because vhost thread was not able to run. It was not able to dequeue packets from the tap socket and hand it over to the guest. So as a result, the tap socket queue was full, and the packets were actually dropped at this point. Packets were being dropped, but whatever was there in the system, like the VM was not able to even process those packets which had been able to enter the system and were there in the tap socket queue. So as a result, one particular side was not able to function at all. I mean, although in certain cases, this other side was able to function, but still the overall throughput was quite low. So for one port, you had some throughput. For the other port, it was completely dead. You were not receiving any packets over there. Okay, so we tried a workaround to kind of get around this problem. So it was not a neat solution, but this is what we tried. So as a part of the soft hierarchy processing, in the tap, this was primarily done at the tap socket level. We actually could, we would check for congestion. So congestion was checked by the queue depth of the tap socket. So if the tap socket was full, right? In that case, we simply disabled the hardware interrupt so that we could not receive any more packets. And so we allowed the packets to be dropped at the hardware level itself for this particular VirtIO interface. And if there was no congestion, then yeah, we continue to send packets forward. And in the vhost processing, we would actually, when we are actually receiving, we were able to receive the packets from the tap socket. We were actually enabling the hardware interrupt. Say when we had subsequent buffers to receive the packets, or like when the vhost thread was able to actually pick up the packet from the tap socket, and tap socket had enough buffers to receive So actually, tap socket had space to receive more packets, so we would enable the interrupts and would allow the hardware to kind of pump in more packets into the OS. So with this, we were able to avoid the situation that we had hit upon earlier, where we had a complete denial of service because the tap socket queue was full and we had to drop packets over there. So even when the tap socket, so now what we had was a feedback mechanism, which we kind of implemented from the tap socket to the physical NIC, right? So when the tap socket could not receive packet, it would actually inform the NIC to not receive any packets on its behalf. It would disable interrupts over there, right? And then subsequently, this would give the vhost thread adequate bandwidth to process the packets from the tap socket and then move it to the guest, right? So once that had been done, we would actually disable we would re-enable the interrupts in the physical NIC to get more packets from the network. Okay, so in this case, as we can see, in the unmodified case or existing design, at a particular ingress rate, the egress rate would actually subsequently decline, right? So it would decline at a very high, when the ingress rate was very high. So initially the egress was there, but then subsequently the egress rate started declining. But with the workaround that we implemented, right, even when the ingress rate was high, egress rate would keep on progressing, right? So it was not a perfect solution, right? But it was a hack, but we were able to avoid that saturation, the system saturation, where we were actually not able to proceed at all. So that was not the case. Okay, so the following slides would actually talk about the proposal or a mechanism to implement what we did as a workaround in a much more better fashion. And the idea is to kind of make this generic for most of the hardware platforms. So although we tried, we are proposing this in accordance to the hardware features that are available on our platforms, but the idea is to make it as a generic architecture and push it there. Okay, so generally what we want to do here is that we want to kind of cut down the layers between the guest word queue and the physical NIC queues, right? So we want to kind of reduce the layers so that packet can kind of seamlessly move from the physical NIC queue to the guest word queue, right? So what we are proposing here is that when the vhost, so we are actually proposing a new kind of a driver framework, which is sitting right underneath the Vhost-net architecture. So Vhost-net can actually register of Rx function. So what this Rx function handle essentially allows us to do is that whenever the hardware NIC is, or the new driver that we're proposing receives a packet, it can directly transfer the packet from the physical queues to the word queue, which are maintained by, or which are actually interfaced with the Vhost-net. And also, in case the buffers available with the hardware NIC for the particular guest VNIC are getting depleted, it can send a notification saying that, like, I do not have buffers. Please replenish buffers in the buffer pool for that particular VNIC. On the TX side, again, we want the vhost thread to transfer the buffers directly from the word queue to the physical frame queues, right? So that's where we register the TX function handle. And then we have the buffer pool management handle where there's an interface through which you can actually get the buffers. So whatever buffers are being seeded by the guest in the word queue, you put them into the buffer queues which are used by the physical NIC whenever a packet is being received. Okay, so this is the new interface driver that we are actually talking about, and this is how the initialization would happen. So whenever this vhost initialization happens, it also registers with this particular network acceleration interface driver, right? So it would interface, it would actually register the Rx routine, and it would also register the congestion handler, right? Which can be used by the network acceleration interface driver to inform Vhost-net and correspondingly to the guest in case of buffer depletion. And say in case of Rx, In case of RX, you can actually, so these are the RX rings which are maintained by the host driver, right? So the Ethernet port has a passing classification distribution functionality which is available. Based on that, it can actually, when it receives the packet, it can distribute the packet across these frame queues. So you have the RX and the TX frame queues. So whenever you are receiving a packet, you can distribute it to a particular RX frame queue, and for the transmission side, like when the packets are copied, packets are actually put into a particular TX frame queue, they can be transmitted from, picked up by the Ethernet port driver and transmitted over the network, right? Okay, so this is this slide is showing that how the Vhost-net driver is going to interface with the new driver that we are proposing. Okay, so this is the TX side where when you receive the packet, you can actually transfer the packet directly from the TX frame queue to the TX ring, which this would be done using the TX function handler, which was registered by vhost thread, because vhost thread is the one which is interfacing with the TX ring here, which is used by the guest virtual NIC, right? Okay, so now with the new architecture that we are proposing, how would the RX handling work? Say a packet comes in. So one important thing, that this buffer pool that we're talking about, this is going to have buffers seeded by the guest, and this the Ethernet port would be able to classify the packet and get the buffers corresponding to the guest VNIC from this buffer pool. So that is an important functionality. So if whenever the Ethernet port receives the packet, it will try to acquire a buffer from the buffer pool, right? If the buffer is not available, then the packet will be dropped here itself. And at this point, it can this network acceleration interface driver can actually inform the guest, asking it to seed in buffers. Now, like we see that the vhost thread is seeding in buffers. The buffers are not there. So another packet comes in. It receives the again, you have the request to the buffer pool to get buffers for this particular packet. So once the buffer is acquired, the packet would be kind of DM'd directly to the guest memory. So because this memory, like whatever buffer was acquired, it corresponds to the guest physical memory that we are having. So directly this can be DM'd to the guest memory. So essentially, this was the architecture that we are actually proposing for enhancing the VirtIO functionality, and which would certainly help VirtIO to deal with use cases with respect to network function virtualization. So this is just to summarize like what I just presented, and as we can see that in certain use cases, vhost.net interfaces can get saturated with high traffic rate, and there is no mechanism as of now through which you can communicate this saturation from the guest to the physical interface. So that is lacking, and that really impacts the overall performance. So with the more integrated solution which we are actually proposing, it is certainly possible that you can provide a feedback and to the physical NIC and improve the overall system performance. And certainly, as I just showed, we can use hardware acceleration for doing this. So I think so this is it for my presentation, and we are open to questions. Any questions? Oh. Mm-hmm.
Can we assign them directly to the guest?
Rings are assigned
to the one-to-one.
So the buffer, you're talking about the buffer pool?
On the rings.
Okay, the ring, the word queue rings, B rings.
So you also like you have a driver default.
Yes.
Or directly the IP rings. So if we assign the rings directly for one particular device, why can't we move these rings directly to the
To the hardware.
These rings will be exposed directly
To the host.
to the guest instead of the vhost.
The data structure of the rings can be different for different NICs.
So you are implementing a driver in vhost. Why you not
It means you have to map additional host nodes.
Yes, but
It's easier to go the other way.
it's easier on its own from the performance perspective. It's not better.
I still could, yeah.
Why not you map directly the rings into the guest memory space?
So rings are already mapped in the guest space, right? So it is a shared memory between the guest and...
It's not remember from the
Oh, these rings. Oh, okay, okay. Yeah, so, I mean, that could be one possibility, but, I mean, we did think about it. Maybe as well.
How about the RX BDE?
What's this one?
So are you sharing these rings between hardcore guest or is the one-to-one?
No,
And underneath, you can have any type of BDE. You can use proprietary BDE or can be pre-used anything.
Is how you split the traffic.
split the traffic. So currently the proposal is to kind of have a 1:1 kind of a correspondence here. We are not splitting. Currently, we are not thinking on those lines. But yes, that's a valid point where you would say that we can directly assign these here. I mean, that could be one thing that we can explore, certainly. But again, the idea is to make this as generic as possible and not hardware specific. So we would need to evaluate as to how other NICs are, I mean, for example, like PCI, SRI, VNICs, how are they, I mean, how can they leverage it, or what would be the case in case of those particular NICs? Yes.
This slide makes it look like that you're essentially dedicating Ethernet port to a given guest.
No, not the port. So it's not the port. It's actually this particular frame queue. It's a queue. So essentially, this port can cater to multiple queues. So you have this passing classification distribution logic in the Ethernet port here, right, which can allow it to distribute packets to multiple frame queues. And each frame queue could actually cater to a different ring in the guest. So it's not actually dedicating an Ethernet port to the guest for that matter, but it is if you have the hardware functionality where you can actually do the passing classification and distribution and have multiple frame queues, so you can use
Using RSS or flow director type of thing to distinguish where the frame is going. And the hardware and the hardware.
Yes.
Okay, so time's up.
Oh.
So
Okay.
there's another report now, and then there's a wait. So you only have to wait like 20 minutes.
Okay. Thank you very much.